Elementary definition.
I have not yet defined it.
No, I'm just asking you. This is a question to all of you. Yeah.
I don't know what you mean. I have no idea, and no, the idea we can talk about it later. Okay.
Okay.
Yeah.
Thank you.
Okay. Yeah. So, any questions other than yeah, so far? Okay. So let's continue. Okay. So this one will. So again, rest of this lecture will be pretty simple. It will not be complicated because you have seen most of it. So let's see. Let's start with sets. So what is a set? A set is nothing but a collection of objects. Right? Collection of objects is called a set. Every object, okay, the set, every things that are part of the set, we call them as elements. Number of objects can be finite or infinite. Okay. So there are some examples. I mean, I'm kind of going to rush over this one a bit. So if you want to slow me down, please shout out. Okay. Okay. So these are some examples of a set of chairs or set of all natural numbers less than 10, number of the set of points in R2, and so on and so forth. Okay. So some of them are set of points in R2 is of course an infinite set. Set of natural numbers is also a finite set on that respect. Set of natural numbers less than 10. Yeah. Now, this is the notion that you have seen. The number of elements in a set is called the cardinality of the set, and is denoted as in this way. If S is a set, the cardinality is with the two vertical lines, one on each side of this set. Okay. Now this is something that please remember in this today's lecture we will be going over it quickly, but the main idea of going over it is that you guys get familiar with this notations, okay? Because these notations will come in almost throughout the whole course, and in case you are not familiar with it, please get familiar with it. Okay. Okay. So usually the sets are written like this, right? It's a collection of numbers. Say this is a set of a set comprising of 1, 2, 3, 4, and 5. Right? You kind of can write it as in a comma separated way between two curly brackets. Whenever you write something between two curly brackets, this is considered to be a set. Okay. And if I want to say that X is an element of a set S, we denote it by this object this way. X is less than S. Not less than, sorry. X is an element of S. And if I have two sets, T and S, and I want to say that T is a subset of S, what does it mean? That by removing some elements of S, I can get T. Or rather, every element of T is also an element of S. Okay? And in that case, we write it, T is like this. This one is T subset of S, and this one means that T is a strict subset of S. Meaning, S surely contains one element that is not in T. The converse is this S is called a superset of T, but this word is not that commonly used, but it might be used some point of time. Now, of course, there can be a lot of sets, right? A lot of kind of sets. For example, this is a set that comprises of 3, 1, 2, 2, 4, 4, and so on. But usually, when we mean by a set, we don't think of or we don't allow repeated elements. Okay, so this having two twos is not something we'll write it as two different types of 2, right? Instead, we think of it as, oh, this is a set of comprising of just 1, 2, 3, and 4. And note that here inside this set, the ordering doesn't matter either. 1, 2, 3, and 4 is same as 3, 2, 1, 4. Okay. So when we say a normal set, I mean this. No element is no element is repeated, and the ordering doesn't matter. But for special cases, we might need them. In that case, one of them is called multiset. If I say it's a multiset, it means that one element, so this is not 1.1, this is 1, 1. Okay, this is 1, 1. And a multiset, the number of times a particular element can appear multiple times, more than once, and you can store them. So here, say we have an element 1 appearing twice. This is the 1 appearing once, and this is a 1 appearing 3 times. So as a set, these 3 are same, but as a multi-set, these 3 are different. Okay. The other thing is that we can have ordered set, a set in which the ordered also matters. So in that case, 1, 2, 3 is different from 2, 1, 3. Okay, so in that case, the ordering of the elements inside the set really matters. Okay. Sometimes it's called the ordered tuple, sometimes it's called ordered set, doesn't matter, some both of them means the same. And you can have ordered multi-set. Okay. Yeah. Now, what all operations are allowed to be done over sets? Of course, you can do a union, which is A union B. Okay. So these are all the elements that is either in A or in B. Okay. Either in A or in B. If anyone where it is there, that should be there in this particular set. So A union B is a set that comprises of all the elements that are either in A or in B. I mean, and it's not an, it has, I mean, if it's there in both of them also, it can be there. Sorry, somebody told complement. What does it mean in the chat? What do you mean? I mean, I didn't get your comment or something. Tonmoy Chandra?
Hello?
Hello? Yeah, you meant something by saying this complement thing?
Complement of a set.
Yeah, it's an operation that we can do. That's what you mean, right?
Yes.
Yeah. I'll come to that. Yeah, I'll come to that. Yeah, so there is the intersection. Okay, and the intersection is A intersection B is a set which has the same thing, but not same thing, but it's all the elements that are both in A and in B. So union corresponds to or, intersection corresponds to and. Okay, I mean it's not something too hard to remember because you can always, you know the definition, you can figure it out. Right. Of course, you can have the complement, and the complement is all the elements that are not in A. Now, okay, what does it mean? All the elements not in A. So, whenever we say a set, we mean there is a universe. There is a general universe in which it is sitting. So, I say a set of all odd natural numbers. When the universe is natural numbers, then I can have the complement is all the even natural numbers. But if the complement, if this universe is a real number, then the complement of set of all natural numbers is something else, right? So a complement is all the elements that are in the universe but not in the set A. Now the last one, this is something that you might not have seen that often. It's called the Cartesian product. So okay, so do I have the definition of Cartesian product? Okay, we will come to Cartesian products after some time. Okay, yes, okay, I will come to that. So this is something that we'll go over it. Okay, so now here is some definition, the kind of pictorial stuff. So you have this is the Venn diagrams. You have A, B, and in that case, it's two circles. There's two blobs. This round blob is A, this round blob is B, and A union B is all the pink things, right? Similarly, here A is this circle, B is this circle, and A intersection B is represented by this intersection, which is the pink. And A complement is if this is A, and the box, this rectangular box is is the whole universe. The A complement is all the elements that are not in A. So it's A complement. Okay. Now there are certain rules about this sets that all of you have possibly seen it and or done it at some point of time, or like, and these are something that will be required later on also. So this is called, first of all, is the commutative law, meaning if I have two sets, A or P and Q, then P union Q is same as Q union P. It doesn't matter which I am putting first, right? A P union P intersection Q is equal to Q intersection P. So this is called a commutative law. Associative law is the same thing, not something, it's a similar thing, where you can say P union Q union R. Now, see, basically, okay, I have a bracketing here. So what means you first you take a union of Q and R, then that set, resulting set, take a union with P. So this is same as P union Q, first take a union of P union Q and then take a union with R. Right? And this is called associative law. And this is the reason exactly why when I have unions only, then I will not necessarily put brackets. Because it's kind of clear. However I put the bracket, basic resulting thing is same. Similarly for the intersection. Okay. Now there is something called a distributive law, and this is a bit more complicated, but it's not too hard. Okay. Now P union Q intersection R is nothing but P union Q intersection P union R. Okay, and similarly you can write it for P intersection. Now, these are law. What does it mean? Although they are law, it is not something that is written on. I mean, it's not like somebody came and told, okay, this is a law that you have to follow. No, these are almost theorems you can think of. Okay, you can prove them that this is true. Okay, you can prove it that these are all true. If you have not seen the proof of them, try to prove it yourself. Okay, and see whether you can formally prove this statement. Okay, best way of proving it is for this kind of stuff is to go through this picture. Okay, in the picture you draw P, Q, and R, and then see what happens. Okay, that's kind of the easiest way of visualizing the proof. And also we have this De Morgan's law, which basically is that P union Q complement is equals to P complement intersection Q complement. Now look at this. Union becomes intersection. Okay, and similarly this. So this is something that also is a theorem that you can prove, and you should be able to prove it using both formally as well as through the pictures. So as a first exercise, something you don't have to submit it as such, I would like you guys to go and prove for yourself all of them, particularly the last two. Okay? Formally prove it for yourself, this statement. Once and for all, you get to see that these are true statements. Okay. Now let's come back to this Cartesian product that we have kind of not told about. Okay. So if I have a set A, now if I take a Cartesian product with itself, A cross A, what is it? This is the set of ordered pairs. So the ordered pairs, okay, where X and Y are in A. So this is, you can think of it as ordered multiset. So XY is different from YX. Or X comma X is not just X. X comma X is X comma X. Okay? And similarly, if I have the Cartesian product multiply the same A n times, it is usually denoted as A to the power n, they are all ordered sets, ordered multisets as you can think of, or ordered sets with repetition of A of size n. Meaning it's just like here it is just two element x and y. Here it is the x1, x2, x3 to x1, x2, x3 to xn, where x i's are in A. Okay. Now, for example, this is a very important example. Say I have a 0, 1. You think of this 0, 1. You understand what is 0, 1? It is just 0 and 1 set. 0, 1 to the n, you have the strings of 0 and 1 of length n. So you are basically, and these are the strings. I mean they are ordered, right? Say 0, 1 cube. How much is that? 0, 1 to the power 3. How much? What are the sets of that? It is 0, 0, 0, 0, 0, 1, 0, 1, 0, 1, 0, 0, 0, 1, 1, right? 1, 0, 1, 1, 1, 0, and 1, 1, 1.
8 combinations.
Yeah. So all the possible combinations that are there. Okay. So by the way, this is a Cartesian product that I have defined for a particular A itself. You can also define for A cross B. By the same thing. Okay, the first element is in A, second element is in B. Okay, and then you similarly you can define for Cartesian product on n different sets also, A1 to n. Okay. Okay, so here are some problems that are there. I think it was picked out and all, and they're very simple stuff. Okay, please go ahead and solve it for yourselves. You don't have to do it, submit it, but if you want us to discuss, we'll be happy to discuss. If not, we can have a chat on that, or the TS can explain it. Okay. This is a very simple setup there. I expect you to try it out and solve it by yourself by yourself. You don't have to submit it. Okay.
So,
right? Yeah.
So, will you be share the PPT?
Yeah,
in
I'll do.
class?
I'll do.
Okay, okay, sir. Thank you.
Yeah, it'll be uploaded in the web page. Okay. Okay, good.
Okay, sir.
Now, let me just quickly go over something else and I will just stop after that. Okay, so there is something called a binary relation. Okay, what is the binary relation? Now think of this S cross S. It's a Cartesian product, right? A binary relation is a subset of this S cross S. It's not all the sets, all the ordered pairs, but a part of it. Okay, any of them is called a binary relation. So, okay, so an R is a binary relation. It's R is a subset of S cross S. So what does R has? The R has something like the of X and Y is in S. Okay, is in R. And we say that in that case X is related to Y. So if X comma Y is in R, we say X is related to Y. Okay. And sometimes it is denoted with this this notation, X related to Y. Okay. Right? And this is a kind of a very simple concept, simple, obvious observations, but it is some extremely powerful concepts that are there, and something that you might have seen it already in some earlier stuff, but here also you will, we will use this thing again and again in various contexts. So there are some kind of relations, okay? So meaning that if you have the relation R, we want to define some more structure. Let's see. There are three types of them. One of them is called reflexive, meaning X is related to X. So in other words, for all X in S, X comma X is in R. Okay, so you can think of it just to kind of to keep in mind, you can think of S to be the set of all people. Okay, and R is the set of all pair of people such that the first person, the person X likes person Y. Okay, so that's a relationship. person X likes person Y. Okay. So of course, not everybody knows each other, so forget liking. So I personally don't like a person whom I don't know, right? So R is a subset of S cross S. Now in this way, is X related to X? Meaning, do I like myself? Or does any person like himself? So that is the reflexive. If that is the case, then we call it as reflexive. If the relation is such that, oh yeah, X related to X always, then the other thing is symmetric, right? If X is related to Y, does it imply Y is related to X? Meaning, if X comma Y is in R, does it imply that Y comma X is in R? Now, this is something that's also there, right? If person X likes person Y, does it mean that person Y likes person X? Yeah, possibly not. But then there are other relationships you can have that. For example, R can be brothers, right? X, Y, if X is the brother of Y. So if X is the brother of Y, Y is the brother of X. So that relationship will be a symmetric relationship. And then you have the transitive relationship, which means if X is related to Y and Y is related to X, does it imply X is related to Z? Okay, X and Y is in R, Y and Z is in R, does it imply X and Z in R? So if an R satisfies, say, this property, then we say, oh, this R is transitive. If a R satisfies reflexive property, we say R is reflexive. Right? Similarly, if R satisfies the symmetric property, we say R is symmetric. And if I have a relationship that satisfies all of these three things, then we call it an equivalence relation. And this is what is denoted as this notation. Okay. So equivalence relation meaning if the R is the equivalence relation, that means X is related to Y. Instead of this this notation, I will say X is these three lines related to Y. Okay? It's the equivalence and the equivalence relation. Okay. Right. So the equivalence relations define your class. Okay. Now this is something like this is the if X is related to Y using this equivalence relation, then we say that oh X and Y are in the same class. If Y is related to Z in the equivalence relation, then Y and Z are in the same class. Note that that means X and Y are in the same class and Y and Z are in the same class, which would imply that X and Z are in the same class. But that is true because I have assumed that the relationship is equivalent. So if X is related to Y, Y is related to Z, then X better be related to Z also. Okay. And so you can define the equivalence class. So for example, we can say that say if S is the set of all, if S is the set of all people in ISI or of all students in ISI, and R is the set of all X, Y such that X and Y are in the same class, in the same in the same course, right? Or something like that. So you basically if X and Y both of them are in MTech CS1, then they are related to each other, right? So then that gives you an equivalence relation. And this the theorem that says that if I have an equivalence relation on a set S, then the equivalence relation forms a partition of this set S. This whole set S is divided into or partitioned into equivalence classes. Now, what does the partition meaning? Partition meaning that the union of all the equivalence classes is the whole set and no two equivalence class intersect. Meaning the intersection is empty. Right? Okay, so good. So this is the property of equivalence relation. And here are some of the problems in the thing of the binary relations that are there. It means this will be posted in the online, so don't worry about it. But these are again the set of questions that that I would like you guys to solve it for yourselves and be prepared. Okay. So, okay, then let me just go over the last section, last thing. So last thing is called a functions. This is again something that you know of. We have seen it. So what is the function? It's the mapping from domain to range. Okay. So f is a function, meaning it's from a set D to a set R. And the particular thing is that for every element in the domain, there must be something, f of x is something in the range. And for every element in the domain, it must be uniquely defined. Meaning it cannot be that f of x is either this or this. I mean, f of x is something, that's it. It cannot be two things. Okay, so that's the function. Okay, and so here is the function that we have. So say here is the function between 0, 1 to r, right? And a big question is that here is an example of a function from 0, 1 to the 5 to r, and I've defined it like this. And one question that will come to ourselves is, if you have this function, how will you be able to represent this function? How will you tell me what the function is? Okay? And this is something that we will think about. Oh, okay. Okay, so I think I will not go further than this. Okay, so there is something here. Okay, so sorry. So either you can give this function explicitly or the function as this kind of formula, right? If you can by seeing it, that you can give these functions in these two different ways. And this is also important, that how a function is given or represented is a very important thing that we will also observe. Now, I don't want to go into it any further. Let's stop here. Somebody told me, wrote a mail, that wrote a chat message that to explain this relation. Okay. So see, I can define what is the equivalence relation. Okay. So equivalence class. Okay. I can say that, oh, if x is related to y using this equivalence relation, then x and y are in the same class. Okay. Now, main idea is that, is it defined? Is it a proper definition? That is the question. That's I kind of hand waved there. I kind of told that, oh, see, if x and y in the same class and y and z are in the same class, then x and z must be in the same class, therefore, right? But why is it the case? Right? So you have to prove it. It follows from the fact that we are dealing with an equivalence relation. Right? So once you have an equivalence relation, so you kind of say that, oh, okay, so the definition of classes makes sense. Okay? Or think of it this following way. Okay? Say, what is an equivalence class of myself? Sorry, of x. What is an equivalence class of x? It is all the sets of the elements in S that are related to x. Okay? So if x is related to y, then y is in the equivalence class of x. If z is related to x, then z is in the equivalence class of x, and so on. So there is the equivalence class of x. Similarly, I can define an equivalence class of y. Similarly, I can define an equivalence class of z, and so on. Right? Now, it so turns out that if you have an equivalence class, then the following things can happen. If you consider the equivalence class of x and the equivalence class of y, okay, either these two classes are disjoint or they are equal. So either equivalence class of x intersection equivalence class of y is empty, or equivalence class of x is exactly equal to equivalence class of y. Okay? And not only that, if you look at all the equivalence classes, okay, you will have this partition coming up, meaning you will have you can say that, okay, so I can partition this S into chunks such that each of the chunks are equivalence classes of something. So maybe equivalence class of X and equivalence class of Y are same, then they form a single chunk, right? And the union of the total equivalence classes is the whole thing. So it kind of partitions this set into equivalence classes. Or in other words, a particular element cannot be in two equivalence classes. Okay. So is it clear what this theorem is trying to say? Okay, so if it is clear, then yeah. Okay, so let me just quickly see what all things are there. Okay, fine. I will, I think, stop over here. Okay, so we have just gone over to definition of functions, and we will take it from here. And in the meantime, just get used to this, all these concepts of equivalence class and all the notation that was defined. Many of you are possibly very much familiar with all of it. So yeah, you guys will be a bit bored for now. So in the next class, we will start from these various things. Okay, well, maybe I can just start to finish this stuff. Okay, here that will be kind of useful. Okay, so we have these functions, right? So we have a function and we want to represent this function. And there are two ways of representing the function. Either you can write it explicitly, right? Like I have done here. Or you can do it implicitly, in which you say, oh, see, f of x equals to x square. And both of them are valid ways of writing. Okay? Now, if you want to represent this function explicitly, then this is what we called as a truth table. Okay, what is it? Say I have this domain. I consider an ordered layout of the elements of the domain D, say x1 to xd. Okay, and then I will say that, okay, my truth table is basically f of x1, f of x2, like this f of xt. Now, if I know the order of 1 to, x1 to xt, then all you need to specify this function to me, all you need to write down the function value at all these points. So this is the most explicit way you can define the function, right? I'm defining function at every possible places. And this is what we call as a truth table of a function. So truth table is basically the function value evaluated at all the points in the domain and written out specifically. So a truth table size is exactly size of the domain, right? Okay, and yeah, so here is a boolean. Yeah, someone want to say something?
Sir, I have a doubt.
Yeah.
Sir, can you please go to the slide which contains the sum, like f1 is 1, f2 is 4.
Yeah.
Yes. So here it is saying like fx is x square, right?
Right.
But is it the only function? Like it can be x square.
It can be the other functions also. It can be other functions.
Yes.
It can be a lot of other functions, right?
Okay. That was the clarification I just.
Yeah.
Okay.
There can be a lot of other functions, but something that you can define a function in a kind of, this is called an implicit definition. We are not telling me exactly what this function is. You're telling me, but not even, but I have to do some calculation myself to find out.
Okay.
Right?
I got it. Yeah.
But the explicit is the one in which this one, right? There's no calculation required, right? And this is exactly the truth table, what we call as a truth table. Okay? Specifying the function as a truth table. Now, if I have a Boolean function, meaning a function that takes in 0, 1 to the n, in a string of size n, and outputs are 0 and 1. Okay, so I can think of the 0, 1 as true, false, left, right, +1, -1, doesn't matter. The main idea is that it takes a two-valued object. The set input is also a two-valued object, and a Cartesian product, Cartesian it by n times, and the output is also a 2 times object, and they can be same, they can be same, doesn't matter. All that matters is the set is of size 2. Both the sets are of size 2. Okay, so these are called Boolean functions. Boolean, because Boolean means it has only 2 values. Okay, it is the name after one of the earlier computer science, earlier logicians, Boole. Okay, of course you might know that in computer science we really deal with this kind of functions almost everywhere, and this is what we kind of work with, Boolean functions. Okay, so let me just stop here with giving you this set of questions on Boolean functions that you guys should try to solve it. Yeah, somebody will have some questions? Hello? Somebody have some questions or doubts?
No, sir.
Okay.
But
Sir,
I
can
can
you?
There's a lot of disturbance. I don't know from where.
Sir, I want the clarification on the truth table in
Okay.
previous slide. Like I didn't understand that how you are saying.
Oh, what is the truth table? Okay, I'll do that. Yeah, hello. Can you mute yourself? Maybe I will just explain because a lot of sound is coming from your side. Okay, so basically, so this is what I mean at truth table. Okay, say I have this function. Then look at this function. Okay, I have 0, 1, 2, 5. 0, 1, 2, 3, 4, 5 is the set, right? If you have to explain me what the function is, okay, and you do it explicitly, a simple thing is that, okay, you just send me a vector containing 0, 1, 4, 9, 16, and 25. Right? I get to know what is what. I know that the first thing that is being told is the function value at 0. The second one is a function value at 1. Third one is a function value at the third point of the domain, which is 2, and so on and so forth, right? So this string, this you can forget. You can just look at this column, okay, and say this is the given the function. So this is called the truth table. So formally speaking, if the domain is x1 to xd, okay, then the truth table is the function value at x1, comma, function value at x2, comma, till function value of xd. Okay, so this is a vector. A vector, each element of the vector contains is a number in R, right? So it is a right. It's a ordered set of d elements from R. Okay, so this vector or this set is called the truth table of this function f. Is that clear? Hello.
Yes, sir.
Okay.
Clear.
Okay, perfect.
Hello, sir.
Yeah.
Chhatri Pratap this side. Sir, this side is available on the web page.
I will put it up in the web page.
Okay, sir.
Okay, so this is a set of functions, and with that, I mean, I think so these are the only set of things that I would like you to work on, solve it before Friday's class. Okay. So by the way, next class we will start on the propositional and predicate logic. So I think if you are familiar and got used to this, whatever has been done till now, I think we are more or less set to jump into some more involved discussions. So is this, no, truth table is not the same as the range. No. Truth table is not same as the range. Somebody asked me, is truth table same as the range? No. Truth table is not same as the range. For example, say look at this one, right? This one, the range is this R. Okay, truth table is not R. It is much smaller. That's first thing. And even if you look at the truth table and say that, oh no, I mean the range to be only those things in R which is of f of something here, right? Even then, the range is not necessarily ordered. The truth table is ordered. Okay, the truth table is this one, which is the ordered set, actually ordered multi-set. So it might be that f of x1 is equals to f of x2. So they both of them can be there. Okay, so if f of x1 is equal to f of x2, we will have say if f of x1 equals to f of x2 equals to 1, then the truth table will be 1, comma 1, comma something. Okay, so this truth table is just a vector. It is not a it's not the range. Okay, it's a ordered set in R to the power n. Okay, an ordered multiset of n, multiset of n. Okay. Okay, good. So yeah, what is the order? What is the order? The order of D. Okay, good. So what is the order of D? Now the order of D, as such, there is no order of D, but it is told that, I mean, truth table is something that is used to kind of pass on the information from one person to the another, or one person to the computer or something. So you start with some order of D. So like, think of it that you know D beginning, you and the computer have discussed, or you and your friend has discussed, and so that, okay, this is the order of D, order of elements in D that I will consider. Okay, and in that order, I will write it. Okay, so that is the order. There is no specific order. But you can always think that everybody in the world has now kind of followed the ordering. Okay, it's comfortable with yours. Yeah, truth table is only for finite. Yeah, truth table is only for finite domain. It is not something for infinite domain. Yeah. Okay. More questions? No doubts? Okay. So which one? This last set of questions. What? I mean, you have to give the number value. Okay. Now you might write us 1 or 2 lines or something like that. But yeah, I mean, so this kind of questions, they are simple enough that I will be fine if you don't necessarily give me the kind of explanation for it.
I mean, just the answers like 2 to the power n, 5 to the power 6.
Something like that is
Like
good
that.
enough for this set of problems. Okay, it's like it's a kind of a trade-off that you have to understand, right? I mean, there will be problems later on where the solution will be not obvious enough. So in that case, you have to explain a little bit more. Okay.
Like in this particular questions, just the answers are okay.
Yeah.
Okay.
So in particular question is question. Like for example, the last question. Okay, it is not very clear whether we will get the whole thing. Okay, what is the value here? Okay.
2 to the power n to the power n.
No.
2 to the power 2 to the power n.
Right. So see, yeah, maybe a one line or explanation is kind of not a bad idea.
Hello, sir.
Yeah. Hello. Yeah.
Yes, hello, sir. I have a doubt on this first question. If you see here, what is the size of the truth table for a function? So our value will always be one of the 0 or 1, right? Whenever we are going from
That
a
is true.
set of.
That is
right?
true.
So in the definition of truth table ahead, in the slides ahead,
Right.
we have a vector of values.
Yes.
So ultimately, that is a finite value, or that will be a vector of values in ordered manner.
So like, look, say, what is the size of the truth table, right? So how big is the domain? How big is the domain, right?
2 to the power n. 2 to the power n.
So the domain is of size 2 to the power n. So that means the 0, 1 to the n has 2 to the power n objects, elements, right? And the function, therefore, you have to specify the function value at all the 2 to the power n elements, right? So the truth table, let's see here. I mean, if you just go for the definition also, domain has been written as x1 to xd, here d equals to 2 to the power n. And the function value will be f of x1, f of x2 till f of x2 to the power n, right? So it's a string of 0 and 1 of length 2 to the power n.
N.
No, 2 to the power n.
No. It's a wrong conception.
Sorry?
Sir, can I tell you something? The vector length of the vectors are n. Length will be n for each vector.
No,
And the
it will
domain
not.
is 2 to the power n.
No, it will be not.
No.
It will be not.
2 power n. It's 2 power n.
No. Domain size is 2 to the power n. Domain size.
Yeah.
Domain
Size
size
of
is 2 to the
Same
power n.
size will be same.
Yeah, truth table will be same as the domain size.
Same size.
Yeah. Yes, it's written here. It's like domain has x1 to xd. The domain, this vector, the truth table length will be t. Okay.
Okay. D.
Okay. Okay, so any other questions, doubts? Okay, so if not, you can, we can stop the class now. Okay, the video. Yeah, the range is only 0, 1. Okay, by the way, somebody is saying truth table is of size 2 to the power n, the range is only 0 and 1. That is true. So it will be a vector of length 2 to the power n with every element in the vector is 0 or 1. Okay? So think of it this way. Okay, just think that you have to tell me a function value of 0, 1 to the 3 to 0, 1. Okay, so there are 8 domain elements. You have to pass on the information to me of what is the value at all the points. How will you do it? Okay, and that is exactly the truth table. Okay, so anyway, so is it clear, Ravindra Sindhya? Okay. Okay, good. So, okay, so let's stop the class now. I think I went through for quite some time. So, I will be uploading the video of recording of this class in next half an hour or so. Okay, and also these slides. Okay, both of them will be available. The link will be available in the web page. Okay, in half an hour time.
Okay, thanks.
Yeah, thanks. Okay.
Thank you, sir.
Thank you, sir.
Thank you.
Thank you,
Thank
sir.
Thank you.
Thank you, sir.
Oh, by the way, do you guys want to discuss here? Should I leave this room, end this meeting, or do you guys want to continue discussing among yourselves? Yeah. Okay. So let me just end it for now. I think you guys are okay. Fine.